Hi, I'm Jingy, and I'm here to present on behalf of work done in collaboration with Will Lee at Adobe Research and my advisors, Sean Fulmer and Manish Argawala at Stanford. Visual content creation, especially of 2D illustrated characters, has been a longstanding medium for communication and storytelling, from comics to infographics to animations. While professional artists have traditionally made these characters come to life in the past, mix and match character creation tools like Bitmoji now provide a low barrier of entry for everyone, not just expert artists, to create custom characters. These tools, like Blush shown here, allow users to quickly and easily produce characters for their needs by compositing different clothing and accessory items together. Although there are typically dozens of these clothes and accessories to choose from, these tools do not support direct control over pose, proportion, or animation of the characters. To allow end users to easily choose and composite accessories, the artwork for these tools is on independent layers. Body layers are layers with artwork that represent body parts, and accessory layers have the mix and matchable assets. And since each of these accessory layers are independent from the body layers, they do not adapt to changes in the body. Let's say I wanted to make this character's proportion better match my own and give them wider shoulders and a longer torso. As you can see, the clothes do not follow the change in this body. And as a result, the character's body shows behind the clothing. We present an automated tool for rigging accessories by applying constraints between the layers such that accessories adapt to deformations in the body. Here, our system deforms the shirt so it fits to the wider shoulders. The idea of rigging is not new, and there are many commercial software tools like Adobe Character Animator and Spline that allow users to manually specify their own rigs for animation. However, this process can be time-consuming and tedious. To address this problem and allow for creating easier deformations, research has focused on automatic rig transfer for humanoid skeletons, manipulating body parameters like height and weight through applying a warp field, and creating single structure preserving links for 2D illustrations. However, none of this prior work addresses our input domain of layered characters and our specific research question. How can we automatically attach accessories to the body such that they deform with the body, in turn making mix and match character creation tools more flexible? Our high-level approach is to construct and infer 4 types of constraints between layers to generate automated clothing rigs, which I will now explain. Our system takes as input the layered artwork grouped into the body and the accessory layers. Complex accessories, such as this shirt, may be further decomposed into separate layers to capture occlusion relationships. From this input artwork, we first automate the construction of a directed acyclic graph, or DAG. The DAG tells us which layers should propagate changes to other layers, such as how edits to the front arm should affect the front sleeve, but not the back sleeve, with the directed edge going from the parent layer to the child layer. First, users manually construct the DAG for the body layers, which means annotating the root node, often the torso. Next, we have an automated algorithm for attaching the accessories to the body in the DAG. For each accessory layer, we check its overlaps with every other layer, both body and accessory. If there is just one other overlapping layer, like the shoe and the leg, we create an edge from said layer to the accessory. If there are multiple overlaps, like with this vest, we consider all layers within some threshold of the maximum overlapping area. We look at the Z order of all these candidate layers and take the one closest to the accessory, in this case, the shirt bodice. Applying these steps for each accessory layer, here is our final DAG for this character. Note that one limitation of our algorithm is that it only creates one edge per accessory, while accessories decomposed into multiple layers may need more edges, so here we also manually connect the sleeves to the bodice. The DAG tells us which layers should propagate changes to other ones, while our 4 constraint types, which I will now explain, tells us how the changes should propagate. These constraints pin the layers together at specific points to preserve different relationships, like the skin staying hidden behind the body as the body moves. That specific issue is largely addressed by our first constraint type, occlusion. Occlusion relationships occur between the majority of clothing and accessory layers, such as the arm and the sleeve. They pin the boundary of the parent layer where it lies within the child layer. Accessory layers may also be constrained at a single point. This is the point closest to the centroid of the child that overlaps with the parent. Layers attached at a single point undergo a rigid body translation, so this constraint is great for accessories that themselves should not deform, like this bow tie. Boundaries shared between layers, common in places where fabric folds over on itself, like the shirt collar, should also remain together after deformation. Thus, layers may also be constrained along these coincident boundaries, which are defined to be within some threshold of each other. In practice, it's 15 pixels. Finally, there are cases where the entire region of overlap between two accessory layers should remain overlapping after deformation. For example, the sleeves and the bodice of the shirt here. And to preserve this overlap, we apply a constraint that pins the layers together along the entire boundary of the overlapping region. And to prevent over-constraining our character, we only place pins around the regions near where the parent body parts attach to each other. So here, where the arm meets the torso at the shoulder and nowhere else. We also automatically infer which constraints to apply between each pair of layers. For each edge in the DAG, we use the following heuristics. If the edge connects a body and accessory layer together, we try to apply an occlusion constraint, which covers the most common cases where accessories fit over body parts. If the edge connects two accessory layers, we apply both boundary and overlap constraints as appropriate. And sometimes these operations result in no points, and in these cases, we add a constraint at a single point. To evaluate our rigs, we demonstrate our constraints apply to a variety of mix and match data sets. First is the OpenPeeps dataset, which show 13 body poses over 40 accessories and across 6 different types of modifications: broader shoulders, a wider belly, an hourglass figure, shorter proportions, taking a step, and taking a seat. The full set of results are available in our supplemental materials. We also demonstrate how our constraints handle custom faces. By default, our inferred constraints are at a single point, but if a user changes them to be regions of overlap, which they may do in the UI, the facial features now themselves deform and stretch. This example highlights how different constraints result in different aesthetic outcomes. We also show our constraints on non-humanoid characters, like these ponies. Finally, we show animations created with our system, such as breathing. Notice how the shirt stretches and the torso expands and lengthens with each breath. And a walk cycle. Notice how first the pants, then the skirt, change with the legs. The biggest limitation of our method is the lack of real-world physics or secondary motion effects. For example, as this character raises their elbow, the kimono sleeve should drape downward rather than remaining stiff. Additionally, we do not currently synthesize new geometries and textures, so patterns on clothing may become distorted, like on this tank top. Our vision is to allow anyone to customize their mix and matchable characters beyond just simple accessory swapping, towards more expressive and representative visual communication. Thank you.